previous class, we discussed about the plane stress loading, axisymmetric loading, followed by the discussion on the effect of confining pressure on the strength characteristic of the rocks, and then we discussed about Mohr's failure theory. So, now the next step is Mohr-Coulomb failure criterion. Mohr's failure theory only mentioned that there is a relationship between shear stress and the normal stress on the failure plane. Mohr-Coulomb failure criterion kind of established a relationship between this shear stress and the normal stress. So, we will today learn that how the Mohr-Coulomb failure criterion can be applicable in case of the rocks. What all are the deviation or what all are the modification that one needs to make in the Mohr-Coulomb criterion which was applicable in case of the soil, so that the same criterion is applicable in case of rocks. So, we are going to discuss all these things in detail today. We all know that the Mohr-Coulomb failure criterion is one of the most popular criterion, and it works very well for the geomaterials, especially for the soils where the failure generally takes place in shear. As per Mohr-Coulomb failure criterion, the shear strength on the failure plane, which is represented by tau f, is related to the normal stress sigma on the plane as this expression tau f equal to c plus sigma tan phi, where c is the cohesion and phi is the angle of friction or angle of internal friction. Now, this equation, it has two separate components. One first component is the cohesive one, which is represented by C, and the second one is the frictional component, which is given by sigma tan phi. Take a look at this frictional component, which is proportional to the normal stress. So, frictional component is equal to sigma tan phi. So, we can say it is proportional to the normal stress. However, this cohesive component is constant and it is independent of the normal stress. We all know that this criteria is quite well applicable in case of the soils. Let us see whether this can be applied in case of rocks or not in this particular manner itself. If it is not applicable in this form to the case of rocks, then we will see that what should be the modification be made to this criteria so that it can be applicable in case of rocks. Uniaxial compressive strength tests, they are very common in case of soils, rocks as well as concrete. Uniaxial compressive strength is represented by sigma c. Now, when the specimen fails, that is at the failure state, the applied load sigma 1 is going to give me the UCS of the specimen, and since it is the uniaxial compressive strength test, all around pressure or the confining pressure is going to be equal to 0, and therefore, sigma 3 will be equal to 0. So, for the UCS test, the state of stress in terms of sigma 1 and sigma 3 is going to be sigma c and 0 respectively. We have discussed this in some of the earlier classes, that in case of the determination of the tensile strength of rocks, one needs to go for the indirect methods like Brazilian tests. What was the reason behind that? The reason was, when we go for the direct tensile test on rocks, there were many difficulties which one faces. The first one was that it was very difficult to conduct the tests in view of the requirement of the special shaped specimen, because when I am saying that it is the direct tensile test, so the specimen should be subjected to the direct pull or the direct tensile force. For such case, the gripping of the specimen becomes very crucial, and one needs to go for the special shaped specimen, which may not be that easy to make in case of rocks. Further, even if you make the special shaped specimen, but then also at the contact point of the loading platen, there is going to be very high stress concentration, which will cause the non-uniformity of the stresses in the whole specimen. And therefore, it was told that direct tensile test on rocks, they are not that feasible to conduct. But say theoretically, if we are conducting the direct uniaxial tensile strength test, in that case at the failure what we will get is the tensile strength, say sigma t. So remember that we are talking about a theoretical condition. So at failure what is going to be is that you will have sigma 1 equal to 0 and sigma 3 is going to be equal to the tensile strength. Now you take a note of this fact here, that I am putting a negative sign here, negative sign. Why? Just to show that it is tensile in nature. So what we are going to do is that to follow the convention that compression is represented with positive sign and tension with a negative sign. So in the two cases, that is uniaxial tensile strength test, which is a theoretical one, and uniaxial compressive strength test, one can draw the Mohr circle at failure. Take a look here. The first figure gives us the idea about the uniaxial tensile strength test. So whatever is the strength that we have is sigma t. This point is 0, so it is on this side of 0, so it is negative, and that is the reason that we wrote that sigma 1 will be equal to 0 and sigma 3 is going to be equal to minus sigma t, because you know that by definition sigma 1 is the representative of the major principal stress and sigma 3 is the representation for the minor principal stress. Now I assume that the Mohr-Coulomb failure criterion, which was tau equal to C plus sigma tan phi, is applicable in the tensile zone also. Then we can extrapolate it in this direction like this, and therefore this will be the tangent to this circle which is shown here, this circle. Now the radius of this circle is going to be sigma t upon 2, because this total is sigma t. This is x, this is also x, and this is also x. And since this distance is c, this angle is phi, as shown here. This distance from this point to this point by simple trigonometry is going to be c cot phi. Now take a look at the other figure, which is for the UCS test. So in case of the UCS test, the value of sigma 1 is going to be equal to sigma c, which is the uniaxial compressive strength, and sigma 3 here, which is equal to 0. Now obviously, because it is on the positive side, so Mohr-Coulomb failure envelope is valid in this case, which will be tangent to the Mohr circle at failure, representing this state of stress. So this distance and this distance, they are going to be same as the radius of the Mohr circle. Similarly, from the simple trigonometry, if this distance is c, this distance from here to here is going to be c cot of phi. Now let us have a look once again on this figure. So if you just try to apply simple trigonometry relationships, what you are going to get is x is equal to c cos of phi divided by 1 plus sine of phi. And therefore, this sigma t, which is equal to 2 times x. Why? Because this distance and this distance, they are equal, and this distance is equal to x. So this sigma t is going to be 2 times x, that is going to be 2c cos of phi divided by 1 plus sine of phi. Similarly, for the uniaxial compressive strength test, we have y equal to c cos of phi upon 1 minus sine phi, and in this case sigma c will become equal to 2 times y, because this distance is y and this distance is y, and from here to this distance is sigma c. So therefore this sigma c becomes equal to 2y, and that is going to be equal to 2c cos of phi divided by 1 minus sine phi. So it's a simple trigonometry that we can find out these relationships. Now what is going to be the theoretical ratio of sigma c to sigma t? Why I am saying the theoretical ratio? Because this sigma t is what we are getting from a theoretical uniaxial tensile strength test. So this is going to be 1 plus sine of phi divided by 1 minus sine of phi, because we saw that your sigma t was 2c cos of phi upon 1 plus sine of phi, and sigma c was 2c cos phi divided by 1 minus sine phi. We just obtained. So from these two, we can get this ratio as 1 plus sine phi upon 1 minus sine phi. Now for a friction angle, of say 30 degree to 60 degrees, this ratio, which is sigma c upon sigma t, it will be in the range of 3 to 14. So you just substitute the value of 30 here in this expression and value of 60, and you will be able to get this range. Now I mentioned to you that it is the Brazilian indirect tensile strength test, which is conducted on the intact rock specimen to obtain the tensile strength of the rock. The condition for the sample preparation was that thickness to diameter ratio should be 0.5 and it was subjected to a diametric load P. Look at this figure. This is that specimen which as it will look like, and it is subjected to this diametral load P. And this is applied along the entire length of the core. The failure takes place due to splitting, and ideally this should split vertically along the diameter into two halves. Then the failure will be at the center of the specimen, and the vertical normal stress at the center is going to be compressive. Please take a look here. If we take an element at the center of the specimen, you see that this vertical, in the vertical direction, you have the normal stress which is compressive in nature, and at the failure you will have the horizontal normal stress, that is this, which is tensile in nature. So as per this author who did this work in 1959, this sigma h or sigma horizontal, which is tensile in nature, that is equal to minus 2p upon pi d t, and sigma vertical, which is compressive in nature, that is equal to 6p divided by pi d t, where this P is the failure load, D is the specimen diameter, and small t is the specimen thickness. So basically you see here that 3 times of the magnitude of the horizontal stress is the compressive stress in the vertical direction. So taking a clue from here, we need to see how we can modify the Mohr-Coulomb failure criterion in case of the rocks, because in case of the soils tensile strength did not make any sense, but in case of the rocks one can rely on some tensile strength of the rock. So the horizontal normal stress at failure at the center of the specimen, it is going to give me the indirect tensile strength, and say I am representing it by sigma t prime. So now we are going to have two tensile strength. One was the one which I got theoretically, which was direct tensile strength, that was sigma t, and another is the indirect tensile strength, that is sigma t prime. The question is, how close are these two values to each other, or how close this sigma t, which ideally it should be the tensile strength of the intact rock, but we are not able to find this out practically. What we can find out is sigma t prime. So the question is how close these two values are to each other. Take a look here at this figure. So this is the Mohr stress circle for the Brazilian test. So what is the state of stress? This is 3 times the stress in this direction. This means that if the stress in the horizontal direction, that is in this direction, is represented by a unit Z, or it is Z unit, then in the vertical direction it is 3Z unit. Now look at this Mohr circle. Sigma 1 here is 3Z and sigma 3 is going to be minus Z. So this is the origin 0, and here you have sigma t prime which is minus Z. So from 0 this is minus Z which has been taken here. Okay, now from this to this, it is going to be, the total distance is going to be what? From here to here it is 3Z plus this Z. So this diameter of this circle is going to be 4Z. So its radius is going to be 2Z, and that is why we have written it like this, that this is 2Z, this is 2Z, and this is also 2Z. Now since this distance is Z, so the remaining from 0 to the center of the circle, which is this point, it has to be equal to Z. Taking the note of all this, take this triangle, let us say this point is B and this point is say C. So take in this triangle, in triangle ABC, what you are going to get is this distance 2Z divided by C cot of phi plus this distance Z. So C cot of phi plus Z, that is going to be equal to sine of phi. Simple trigonometry. Now just simplify this. So what we are going to get is 2Z equal to, say C, I can write here as cos phi upon sine phi and multiply it by sine phi, plus another term you have as Z sine phi. So this will get cancelled out, and this is going to be C cos of phi plus Z sine of phi, or we can write here as Z 2 minus sine phi is going to be equal to C cos of phi, and therefore Z will be equal to C cos of phi divided by 2 minus sine phi. So this is what is the expression that I am going to get for the Z. So this is representing, you see here Z is representing the tensile strength. So the tensile strength in case of the Brazilian test is going to be given by this expression, which is C cos phi C cos phi divided by 2 minus sine of phi. Now what will happen to the magnitude of the indirect tensile strength? This is going to be sigma t prime, which is equal to Z. See, I am talking only in terms of the magnitude, therefore I am not putting a negative sign here, which we just derived. It is C cos phi divided by 2 minus sine phi. Now theoretically, this sigma t prime is less than sigma t. Please compare this sigma t expression which we obtained earlier with this expression of sigma t prime, and you will get this. Now this is theoretically true provided Mohr-Coulomb criterion is valid in tensile region as well. So we need to be careful about it that the one which we are obtaining from the Brazilian test is less than the direct tensile strength of the rock. Now theoretically, the ratio of sigma c to sigma t prime of Mohr-Coulomb material is going to be given by this expression. You see that sigma c upon sigma t prime is going to be equal to, we derived it as 2c cos phi divided by 1 minus sin phi. Earlier we derived this, and just now we derived the sigma t prime, which is c cos of phi divided by 2 minus sin phi, and since it is in denominator, so this term 2 minus sin phi will be in the numerator, and here you will have c cos phi. So c cos phi will get cancelled. So what you are going to get is 2 into 2 minus sin of phi divided by 1 minus sin phi. So this is what is the ratio sigma c upon sigma t prime we are going to get theoretically for a Mohr-Coulomb material. Now for a friction angle of 30 degree to 60 degree, this ratio work out to be 6 to 17, and tau f is equal to c plus sigma tan phi is basically meaningless when sigma is tensile. So this is valid essentially when sigma is positive or compressive in nature. For these soils, this Mohr-Coulomb criterion is mainly used as this sigma is greater than or equal to 0, but rocks can carry some tensile stresses, and in view of this, if we want to apply Mohr-Coulomb failure criterion in case of the rocks, we need to make some adjustment in the tensile region. As far as the compressive region is concerned, we do not have any problem. There are better failure theories which are available for rocks under the tensile stresses, and one of such theory is the Griffiths theory. Although this is beyond the scope of this course, but this is just for your information that better theories than Mohr-Coulomb failure criterion, they are available to represent the strength characteristic of rocks under tensile stresses. Now, since we have to do some kind of adjustment, that is what we saw. What kind of adjustment should it be? So, you see here in this figure that it is the simple extrapolation of the criterion. So, this criterion was like this in the compressive zone. So, I will just simply extrapolate it in the tensile region like this, where the minor principal stress is less than 0. That means this is your 0 point in this zone. And obviously, this minor principal stress cannot be less than the tensile strength of the rock, and therefore, the limit to this extrapolated line is going to be given by this vertical line, where this is the state of stress represented by minus sigma t. In this figure, there are 3 more circles which are simulating. Number 1 is the uniaxial compression test, in which sigma 3 equal to 0, which is here, and sigma 1 equal to its UCS value, which is sigma c. The second one is the Brazilian tensile strength test or the indirect tensile test, which is given by this circle, and we have seen that in that case you have sigma 1 as equal to 3 sigma t and sigma 3 is equal to minus sigma t. Then the third circle is the representation of the state of stress in uniaxial tensile test, which is the direct uniaxial tensile strength test, and in that case we have the sigma 1 is equal to 0 and sigma 3 as minus sigma t. Assumption which is involved here is that the tensile strength from the Brazilian tensile test and uniaxial tensile direct strength test, they are same. Otherwise, we will not be able to draw this figure. Now, take a look at this curved dash line, which is the actual envelope in the tensile region. But what we are doing is we are extrapolating this Mohr-Coulomb failure envelope in the tensile region and making a tension cutoff here corresponding to sigma 3 equal to sigma t, that is in the negative side. So, the actual one is this dotted one and the simplified one is this one. So, we can see that from the figure itself, it is clear that the simplified Mohr-Coulomb extrapolation, it overestimates the strength in the tensile region, that is this region. So, one needs to be careful about this issue, because whatever that you will get from the Mohr-Coulomb failure criterion, which has been extrapolated in the tensile zone, you are going to get better strength characteristic because it is overestimating the strength. So, one needs to be careful about the choice of the values of C and sigma t. It has to be used judiciously. So, basically this tensile part or the left side of this Mohr-Coulomb envelope is worrisome. We need to be careful about it. Now, take a look at it here. So, we will apply this tension cutoff and then we will try to see that what can be the situation here. So, sigma c is given as 2c tan of 45 plus phi by 2, which is equal to 2c cos of phi divided by 1 minus sin phi, and also it can be written as 2c square root of 1 plus sin phi upon 1 minus sin phi. This at failure sigma 1 can be related to sigma 3 by this expression, which is sigma 1 equal to 2c tan of 45 plus phi by 2 plus sigma 3 tan square 45 plus phi by 2, or sigma 1 is equal to sigma c plus sigma 3 tan square 45 plus phi by 2. Sigma c, you can see that here it is 2c tan of 45 plus 5 by 2. So, I just represent this first quantity by sigma c. So, we will have the subsequent discussion with respect to this Mohr-Coulomb failure criterion in the next class. So, what we discussed in today's class is with respect to the Mohr-Coulomb failure criterion. We saw that it is quite widely applicable in case of soils, and in case of the rocks we need to make some adjustment as far as the tensile region is concerned to apply this criterion in case of rocks. So, we will continue with this discussion in the next class. Thank you very much.